Good morning, everybody, and welcome to our webinar today. Today's webinar will be Hipot Testing 102. Before we get started, a couple quick comments here, especially for you guys who've never used GoToMeeting in the past. There are several utilities that you can use in the event that you might have a question or you may be having problems with the presentation. Perhaps the slides aren't catching up, perhaps you're having some audio issues. If you are having problems with the presentation itself, audio, slides, things of those nature, please use the chat utility and address those to Jim Kennedy, and he'll be able to help you out. If you have questions about the webinar itself, questions about the material, please use the Q&A utility, and we have some people here who can help answer those questions. Any questions that perhaps we were not able to get to during the webinar, we will save some time at the end of the webinar to be able to attempt to address those, especially if we feel those questions might be beneficial to the group. This webinar is being recorded and will be available to view usually within a day on our website. So if you go to asresearch.com, go to support, look up webinars, and we have an entire webinar archive, and you can get those not only from this one here, but for the past year, I believe we keep them. If you want a copy of the slides, for the presentation itself, email Jim Kennedy, jimk@asresearch, and he can send those out to you. All right, great. That being said, let's get started. So I just want to do a quick recap here because this is called Hipot Testing 102 for a reason. The last session in April was Hipot Testing 101, and that was covered by my colleague and application engineer, Syed Abidi. He did a great job, and hopefully you were able to attend that. If you weren't, and you're jumping just into this one, if you don't have a lot of familiarity with Hipot testing, I would highly recommend you go back and watch Hipot Testing 101 because you really dives into the basics. I'm not really going to do that here. I'm pretty much going to assume that you've seen Hipot Testing 101, or at the very least, you know the basics of Hipot and dielectric withstand testing. If you do know the basics of it, you should be fine to follow this material. Otherwise, you may want to go back, view that archive, and then watch this one at a later date. As I mentioned before, we are recording this, and it will be available on our website, so it's not like you're missing out if you happen to choose to go that route. So here's what we covered last time. Understanding the Hipot test, basically, we started out with what is the test, and what is it exactly testing. And as you have learned from the last one, it's basically just applying force to insulation to make sure it can handle it. Make sure that the product's going to be safe when it goes out the door, and that when somebody plugs it into the wall and they touch it, it's not going to kill them. You're just basically making sure the insulation is solid and that it's sound and that you've tested the integrity of it. We've also talked in the last time about the Hipot test failures, leakage current and dielectric breakdown. And then we talked about the test parameters and the AC and DC Hipot tests. One thing I did want to note is in the last one, I know that Syed delved very in-depth into the AC versus DC Hipot testing. You may have noticed if you looked at the topics that were on the archive or the webinar upcoming events for Hipot Testing 102 also had AC versus DC Hipot test listed. Well, since he covered that so in-depth, I will not be covering that today. You'll get plenty of an earful of it if you listen to the last webinar. Instead, I'm kind of going into a bit more on arc detection because I know that arc detection was a question that came up several times in the last webinar. So I felt it would be better for me to skip over the AC/DC since we already covered that in the first session and then go into something that people had questions about. That being said, this is where we're going to take it to the next level. So we're going to cover 4 main topics here today, and we have a lot to cover, so I'm going to run through this material relatively quickly, hopefully not too quickly that you guys aren't able to see all of it. Once again, you can go back and watch it, but we do have a lot of ground to cover in this 45 minutes to an hour, and I usually like to leave a few minutes open at the end for questions. So first we're going to talk about leakage current. I know that you guys talked about that last time, but I want to talk about leakage current limits and determining limits because I think that's something that is not covered very well with regards to the safety standards and the safety agencies. Then I want to talk about 500 VA testing because it is very important, especially for type testing or prototype testing, something that you would do in a lab on a prototype or a run or first run of products. And that's as opposed to production line where it's getting done on every single product that comes down the line. So what is 500 VA testing? it's important to define it, and then that kind of plays directly into line versus load regulation for a Hipot tester. And lastly, we have to ask ourselves, is it really necessary? And that's something we'll talk about more in depth. Then I want to get into something that I feel is very important when it comes to Hipot testing. I know you guys talked about in the last session breakdown and leakage current and all that good stuff, but I want to get more into fault detection itself. What is the unit detecting? What is your Hipot detecting? What is it finding out? What is it telling you? How does it take that information on a failure and spit it back to you, and how accurate is that? So we're going to talk about the types of failure detectors, specifically our instrument failure detectors, because I can't really speak on competitive units detectors, but I would imagine they were probably very similar. And then, as I mentioned before, we're going to talk about arc detection, because we got quite a few questions on this. And then finally, I want to run over some features of our Hipot testers that after going through these first two topics, these features, you're probably going to find them very useful. I've done this with some other webinars, and I had people come up to me afterward and basically say, I didn't even know my Hipot tester could do that. Well, that's exactly why I want to talk about it, because I want you to know what capabilities you have on these things. Even our very base models have some pretty neat capabilities that you can take advantage of either for functional testing or for operator safety. So that being said, let's get into it. So before I get too much into leakage current limits, and I know you covered this last time, but let's do a little brief recap here. Let's talk about leakage current itself. So what you're seeing on screen right now is that is just the front panel shot of one of our Omnia 2 instruments. And what it's simulating here is an AC Hipot test. Now on the diagram on the right, just imagine the Omnia is what's represented as the source. That little circle with the wavy line in it is our Omnia. And we are applying high voltage to a DUT. And for the most part, a DUT can be represented by this very simple circuit. So what we have here is we have three portions to the current. Leakage current is basically just the stray current that is flowing through the insulation itself. So as you can see here, we have a total current, and then that total current is comprised of two separate values. We have what we would call our capacitive current, or maybe our reactive current in this circuit, and then our real current, or our resistive current. Now for a Hipot test, the vast majority, in most cases, not all, but for most cases we deal with, the vast majority of leakage current is going to be the capacitive current. Because, I mean, if you think about it, when you run a Hipot test, what are you doing? You're applying high voltage to all of the current-carrying conductors, all shorted to the high voltage point, and you are returning on either a chassis point or a grounding circuit. So basically, all you're doing is you're taking two conductors and you're sandwiching the insulator in between them. And that insulation, or that dielectric, is the insulation of your product. So you're really just creating a capacitor. Yes, there will be some resistive elements involved in some products more than others. In fact, we do have customers who straight up just test resistors, and that's, as you can imagine, not going to be much of a capacitive element involved. But if you look at that perform test screen on the left-hand side, I actually ran that on a product, and you can see the total current, which is the 2.56 milliamps, and it's starting over here, but you'll see it build up as it ramps up. The 2.56 milliamps is the total current, and then you can see on the right-hand side there we also have a real current measurement, which is only 0.78. So that means of that total current, only 0.78 of it is real, and all the rest is capacitive. That is very common to see with a Hipot test. So that's important to remember moving forward. So really, how do we set leakage current limits? It's tricky because most standards don't actually give you limits for leakage current values. There's a couple of exceptions. There's some standards out there that do give you some leakage current limits. IEC 60335 for household appliances is one of them. They basically say 5 milliamps for most cases, and then they give an exception to 30 milliamps for devices that might just be more high leaking as a natural part of how it operates. But this is a good way. This is generally the way that I will do it. I think it's a good rule of thumb. Obviously, everybody is going to be a little different in this regard, but I think this is a very solid method for doing this. So you can see it's basically 4 steps. It's perform and record, calculate, add, subtract. That's really it. You don't need a degree in calculus to figure this out. So what you want to do is, if you're first starting to run Hipot tests on something, find a known good DUT. Find something in your arsenal that you know to be good, you know to have been constructed solid, If you can, multiples are even better. But perform Hipot testing on these known good samples. And you're going to get a leakage current value from your Hipot tester. Hopefully your Hipot tester has a way of indicating leakage current. Maybe if you have an older school one, it doesn't. In that case, you're probably just dealing with breakdowns anyways, which is fine. But I still think monitoring leakage current is a very good idea because it gives you information as to the quality of your insulation. So yes, being able to detect a breakdown is obviously important for a Hipot tester, but most Hipot testers nowadays will also give you a leakage current reading, and that can be very valuable information, especially if you're recording and keeping track of results. You may even be able to trend over time and see if leakage current in your product is increasing, and I've seen a lot of our customers do that. But anyways, after you take all those samples, you calculate the average leakage current from all the samples that you just did. So you've performed those tests, you've recorded the values, now you've calculated an average. Now it's just a simple matter of addition and subtraction. So then take 25% of this average and add it to the average value. That's your high limit. Do the same thing on the other end. Take 25% and subtract it from that value, and you get yourself a low limit. And that gives you pretty good head and a floor and a ceiling as far as setting your limits. I've run into customers of ours who are a little bit more stringent than that, and they have to have tighter tolerances. That's fine. Every company might do it a little bit differently, but really what I'm saying here is if you really have no idea on what your limits should be, first of all, that wouldn't surprise me because, like I said, the vast majority of product safety standards, when they talk about dielectric withstand or Hipot testing, they don't mention anything with regard to leakage current. All they usually say is no breakdown shall occur, no shorts, no surface tracking, stuff along those lines. They don't really give you leakage information. So you certainly can use this method. So let me give you an example. Say I test 10 DUTs and I calculate that the average leakage current is 5.5 milliamps. Well, using that, my limit's going to be, I just take my 5.5 average times 0.25 and I get 1.375. I'm just going to add that to my 5.5 and set my high limit for 6.88. A lot of ours, I don't know if they go actually down to the 0.01 decimal place or the hundredths place, but even so, you could say 6.9, round up. We're just taking an average here anyway, so you don't have to be super precise. And then the low limit, obviously you can see I did the same thing. So now I have a window. I can go in and I can program my Hipot unit and say, all right, I know if it strays outside these values, it might not be a failed product, but it's probably something we should look at because it seems a little bit out of the norm from what we've been testing. So this is something to definitely keep in mind when you're running through setting up a Hipot testing procedure. Okay, so now that we've kind of gotten that out of the way as far as leakage currents is concerned, because I know that wasn't covered last time as far as setting up a good method for calculating that, I want to talk a bit about 500 VA Hipot testing. Maybe you've never run into this before because you literally were just handed a Hipot tester and said, hey, this is going on the line, make this thing work. But if you're an engineer who's had to spec a Hipot tester, there's a really good chance you've run into a 500 VA requirement because there are a lot of international standards out there that call out for this for the type testing, even some of them for production line. But just to give you a rundown here, what's the VA rating? Well, it's literally just the power output rating of the Hipot transformer. You take, as you would with any power supply or anything else, voltage multiplied by total max current, or the capable current that it can read, and you have yourself a VA-rated Hipot transformer. There are certain standards that require the use of a 500 VA Hipot transformer. It has to do with energy and breakdown. Really, why would you require 500 VAs on a Hipot transformer? And this goes way back to when Hipot testers were really basically just a big transformer that you would use to apply voltage. Originally, so I believe this was required to ensure that the Hipot voltage output remained constant under varying line and load conditions. And I'm going to talk about that more in a minute. There are also applications where even if the standard doesn't call for it, you may need something that's got a little bit more trip current capability. Let me give you an example. 2,000 meter length of cable. We run into this with cable manufacturers quite a bit actually. They might want to test a 2, 3, 4, 5,000 meter length of cable. That might just have 60 milliamps of leakage just in and of itself. I mean, if you think about it, it makes sense. So you have cable, and it's a certain number of picofarads per foot, and now you're multiplying that by the thousands. You do a quick calculation to figure out how much leakage current you're going to have because of the capacitive reactance, and you'll see, oh my goodness, I'm going to have 70 milliamps of leakage current, and this Hipot unit we're thinking about speccing tops out at 20 milliamps. I can't tell you how many times I've gotten a call from somebody where they're like, hey, I'm running this Hipot tester and it keeps saying fail, but I'm pretty sure these are known good cables. The first question I always ask is, what model do you have? And then I can find out what the maximum output is. And sure enough, they tell me, oh, I have model XYZ. Well, that one tops out at 20 milliamps. You're not failing. The Hipot tester is telling you that you're going over what it can read. So as far as the Hipot unit is concerned, it is failing, but as far as the integrity of your insulation is concerned, you in fact are not. You don't know if you're failing or not because you can't read enough. So in those cases, you might need 100 milliamps or more, although the 100 milliamps is the most we manufacture. Most associated research instruments have a 5,000 volt output. Thus, the instruments have a 100 milliamp trip current rating and 200 milliamp short circuit current rating for all of our 500 VA models. So let's get a little bit more into this whole discussion on line versus load. But before we do that, we're going to give you guys a quick poll here to ask about this 500 VA testing, because this is something we run into on a constant basis. So we want to know from your side, what are you guys using? And I'll give you guys a minute or so to do that.
Hey, Nick.
Yes, sir.
When you get the chance, or when we start up again, I do have a question from one of the attendees. It'd probably be good to ask now.
Excellent. All right, I think the poll has closed, so we should be back on air. We had Pete Stevens, who's helping out with the questions, said that a really good question came through that would be worth it for the group to hear. So yeah, let's dive into that.
It's actually in reference to one of the previous slides in reference to like setting current limits. That 25% multiplier, what's that based off of? What's the basis for it?
The basis, that's a good question, Pete, and I knew that somebody was probably going to ask that. The actual basis for that, well, this goes back to us dealing with certain of our customers and some of the requirements they had from their customers. So basically this customer said, hey, we're doing this testing and our customer says we need to be within this and this limit. Their limit in that particular case was 25%. It just so happened to turn out that that number worked very well for several other applications, so we just kind of latched onto that and adopted it. So it came about for us from personal experience in going out into the field and viewing some of these customer documents and requirements. But as I mentioned before, there might be people out there who have much tighter requirements. I've dealt with medical companies who will have to have a plus or minus 5 or 10% swing. It really depends application to application. I like to give it a little more headroom just because when you're dealing with something like high voltage, the nature of it can be quite erratic. So that gives me a little bit more playroom, but again, that came from a personal experience. Good question. So moving on here, we had been talking about this 500 VA Hipot testing, and what I wanted to show you guys is kind of by the numbers here. I had mentioned to you before there are certain standards that say you need them, and here's a few of them. These are standards. These are not small standards. These are standards that cover a very wide base of products. I mean, just think about household appliances. Anything that you can plug into the wall that you can use in your house falls under that 60335 standard. 61010, equipment for laboratory use. Almost any type of equipment that can be used in a lab falls into that standard. So we're not talking about a small number of products here. Thus, there are a lot of manufacturers who, as a result of the language in these standards, would have to buy a 500 VA unit. And here's the language that you'll see in the standard, should you see this. generator, talking about the Hipot test generator in this case, shall be able to supply a power of at least 500 VA. And then it gives specifics as far as ramping up the voltage and whatnot. 60598-1 for luminaries. That the voltage is essentially substantially sinusoidal. That's pretty common language as well. That the short circuit current shall be at least 200 milliamps, and the overcurrent relay, i.e. the trip current, is not less than 100 milliamps. It should not trip below that. So basically, that's, again, a 500 VA unit. And then, of course, with 60335, it's pretty much the same language, 100 milliamp with 200 milliamp short circuit current. So if you're designing a product and you are designing to one of these standards and you're testing in the lab in your process design, you have to buy a 500 VA Hipot unit per the language of this standard, no exceptions. Now, in production, that's a little bit different. Some standards state that you still need to use 500 VA production, but there are a lot of them that say you do not. That you don't have to use a 500 VA tester. You basically can use a Hipot tester that'll work for your needs for production. Again, it depends standard to standard. A lot of these standards don't say anything with regards to routine production line testing. They kind of leave it to the manufacturer to use risk analysis to determine what needs to be done. But I just wanted to show you some language in the standards, and I'm sure some of you out there may have even seen this information in the past. So where did this all come about? Like I said before, we were talking about being able to actually maintain the output of the Hipot tester under varying line and load conditions. And here's why. If a Hipot circuit is too heavily loaded or the input voltage drops, the Hipot test voltage can dip. This is a problem because if your Hipot test voltage is 800 volts, but your customer says, hey, you need to test this at 1,000 volts, you are now not testing it properly. Or, which can even be just as bad, let's say your line voltage is running high, and now your Hipotter is outputting 1,200 volts. You may actually be compromising the insulation on a product instead of actually testing it to make sure it's safe for use. Now what you've done is you've compromised the insulation, said it's okay, and now sent it out where it could actually cause a problem down the line. So that is for what I would call an unregulated Hipot output. A lot of the very old instrumentation was unregulated, and I think that's where these rules came from. Now, a lot of times now, though, all of our units, I can't speak to a lot of our competitors, but every single one of our units has a regulated Hipot output. We have voltage feedback loops, and we're monitoring the voltage on the output to ensure that no matter what the load condition or the line condition, and we have specs too, obviously, with the input, you have to stay within plus or minus 10%, but within that plus or minus 10% swing, this unit will maintain its output voltage no problem. So it's important to know what kind of Hipot unit you're working with, because if you have a regulated unit, you're going to get good voltage maintenance on the output, but if you don't, you really have to be careful. So let me, bear with me here, guys. I got to share some videos that I took here of a really old school Hipot tester, and I think this will be kind of cool to see. Let me just pull up these videos. And what I'm going to show you here is two different videos. One is from this very old unit that will show you regular, like a standard load. All right, so here comes the video. Let me just pull it up here. Give it a second because I know it can take a minute to for you guys to be able to see the video itself. So let me open the media and then I will share it. Okay. Okay. Just to make sure, Jim, can you see that? Could you type me a quick, can you see this panel shot of this video?
Yeah, Nick, no, we're not seeing it, so it doesn't look like you're currently sharing it.
Hold on.
We were seeing it, and then it quickly disappeared. There we go. It's back on now.
Back on. Okay, good. All right. Sorry about that, guys. Okay, so what I have here, as you can see, an old school Hipot tester. I'll push play now. And what I'm just showing here is that I have a very simple DUT. This is a standard load, so I know that this thing has very low leakage. So what I'm going to do is come over to the Hipot unit, and I'm going to turn it on an AC output, flip it up, output on, and I'm going to crank it up to 1,000 volts. As you can see, no problem. Maintaining 1,000 volts without issue. Great, so that wouldn't be an issue, right? However, now let's look at when we heavily load something. Take a second for this video to pop up. And it's the same unit, but what I want to show here is what I did was I took a capacitive and a resistive network. As you can see there, we are on the AC output. Same unit I was working with in the previous example. But now I have a large capacitor in parallel with a resistance. You can see I don't have the return on there at the moment. I actually have an associate off to the side wearing high voltage gloves, and when I give him a cue, he's actually going to put the return on there to complete the circuit. But the reason I'm doing this is because I want to first show you that I crank up the voltage to 1,000 volts, and then I cue him to go ahead and put the circuit on there. And you can see we have a pretty heavy dip right there in voltage. Actually, it must have been a perfect match there because it dipped by about 50% exactly. But this was the problem with all of these old Hipot units. Obviously, yes, there's a breakdown and a leakage indicator. As you can see on that unit, it wasn't working. Like I said, it's an old unit. But I just wanted to, the reason I brought that up is because I wanted to point out how this can affect your results when you're running with these old unregulated units. So, an important note here is that some standards include exceptions to this 500 VA requirement. UL 1598, luminaries, for clause 19.20. If the output of the test equipment is less than 500 VA, the equipment shall include a voltmeter in the output circuit to directly indicate test potential. That way there are no surprises. This is exactly what I was talking about. So really read your standard carefully. I mean, in the end, you have to follow what the standard says. If your standard says you need a 500 VA unit, you're going to have to suck it up and get a 500 VA unit. But the one thing you should really look at is if your standard does contain an exception to the 500 VA rule. And no matter what standard you have, it's going to be very similar language to what I have here. And also, keep your eyes posted down the road, because I've seen a lot of standards bodies working with guys like us to change these 500 VA requirements. In some cases, perhaps they're still necessary, but in a lot of cases, they're realizing that the technology has caught up, and that a lot of times 500 VA really isn't needed anymore as long as your Hipot tester can maintain the voltage output. So there could be some adoption in various standards in the near future that remove this requirement. So we'll see what happens, but keep your eyes peeled. So hopefully you got some useful information off of 500 VA testing. It's something that comes up quite a bit. Okay, so we've been talking about testing. We talked about leakage current. We talked about energy requirements on a Hipot transformer. Now let's talk about something that I feel is a very important topic, and that's failure detection. How is the unit detecting failures? What is it detecting? Are there multiple types of detectors? Yes, there are multiple types of detectors, and let me give you, this is a brief rundown of the different types of detectors. First and foremost, our most important one, our all-encompassing detector, is our breakdown detector. Obviously, a Hipot tester is designed to detect a failure of insulation, or what we would call a breakdown of insulation. So, as you might imagine, this is a pretty important detector. So our breakdown detectors actually act on a 400 microsecond interrupt. It's very quick, and that's the same for both shorts, direct shorts, and breakdowns. Those are different, by the way, and I'll talk about that more in a minute. Then, of course, we have our leakage limit detector. This goes back to what I was talking before on leakage currents. Say you set a high limit and a low limit. Well, the unit is going to look at this, and then obviously if it strays outside your window of leakage operation, you're going to get a failure. This one's a little bit slower since it's not like it's detecting like a catastrophic event. If your installation does fail, even if you have leakage limits, the breakdown detector takes precedence. So even if you have, say, a high limit of 5 and a low limit of 3, if you get a true breakdown, the unit's going to find that right away. It's going to give you a breakdown failure. But the leakage one works off the sample rate of the unit. It's just 100 milliseconds. So the unit samples every 100 milliseconds for the leakage limit, and then it gives you back those display. Every 100 milliseconds, you'll see an updated leakage value. So if it doesn't catch it on the first one, it'll catch it on the next sample. Then you have our arc detection, which is designed to detect an arc failure. And it's important to note that in order to use this on our units, this is something that is specific to our units. I'm sure other units out there have a similar feature, but this is our arc detection feature that is not replicated on any other instrument. Associated Research has these. The arc detection has to be turned on in order to operate. This isn't like another breakdown failure where it's catching it all the time. You don't turn it on or off. It's going to catch it every single time. Arc detection is a little bit different, and I'm going to talk about that in depth in a minute. So each detector has a priority. Shorts and breakdowns will always be detected with a high-speed interrupt, as will the arc detection if you actually are going to use it. The leakage limits will trigger if a failure if the current goes outside of that window. And then arc detection is only going to trigger if you have that on, but actually arc detection triggers in a similar fashion as breakdown. So here's what's going on in our instruments. Just imagine that on the upper left hand there, you see a transformer. That's the Hipot transformer, and you can see the HV output going out to the DUT, and then on the return line, we have some detectors here that communicate directly with the CPU of the instrument to give information and determine if something is going to be a failure or not. So I'm going to start at the bottom there where it says overload. Overload, that's our short and breakdown detector. That's the quick one I was talking about. That's why it says high speed. That's that 400 microsecond interrupt. So we're talking about, when it says both frequencies, what I mean by that is it's looking at high and low frequencies. And when I talk about arc detection, you'll understand that a little bit better. But it's looking at one threshold. Basically, it's looking at the maximum capability of the unit. It's looking at various frequency ranges and saying, all right, for example, if the unit's reading a breakdown, what it's seeing is not only did it go above the leakage current capability of the instrument, but also it's detecting these high frequencies, these very high frequencies over about 10,000 hertz, which are indicative of the buildup of corona, which can be used to detect arcs as well. So that is what it knows. Hey, I saw these events both happen. We have a breakdown here. Whereas the leakage current meter, and that's the low frequency one, what I mean by that is that's your standard 50, 60 hertz, whatever you're powering your product with. It's a bit slower. Your 100 milliseconds right there, just to make sure that you're staying within your windows, and if you're not, it'll fail. And then arc detection, which is high speed as well, it has to be in order to catch these very quick events, which is our high frequency detector. And we'll talk about that more in a minute. So let's look at a couple examples of failure detection, because I just threw a lot of information out there at you guys, and I want to make sure that you understand the difference of what I'm talking about. So let's first look at a breakdown failure. And Jim, can you see this video okay?
Yeah, Nick. Sorry.
Right,
Yeah, Nick. I'm sorry. I was a little slow to unmute my phone, but yeah, we're good.
Oh, no, that's fine. I thought you had typed something in there, but that's okay. So, okay, good. So what we're showing here is I have a unit set up for 5,000 volts with a 5-second ramp. You'll notice what I have there, there's a very small gap between high voltage and return. I did that on purpose because I want to break down the air. So I'm going to test. I'm going to ramp up. It's going to snap over on that lead, and it gives us a breakdown failure, as it should. Because what we had there was an arcing event, high frequency and low frequency, and it picked it up because we had a breakdown of air. Air is an insulator too, so all we were showing there is a breakdown of air. Now, I want to compare that with what I would call a short failure. They're not the same thing. So again, I have the same test here, But as you can see, I just directly clip the leads together. And boom, right away, it gives a short failure. You can see it on the screen there. It says short, and the unit knows the difference because it didn't see that high frequency noise that you would expect to see with a breakdown. It literally just saw a direct short between the high voltage and the return lead, so it knows the difference. And then, even different yet, I want to talk about the high limit failure. So what I have here, I'll pause this for a second. I have my high voltage and return across a capacitor, a rather large capacitor, one that I know is going to cause my instrument to go over its 50 milliamp limit right there. So you can see it's starting to ramp up, but you'll notice on the screen there, now it says high limit T. And it says that because we went over, as you can see on the screen there, it's telling you that the total and the real current went over 50 milliamps. It didn't register it as a breakdown or a short. It knew, hey, I didn't see this high frequency event. However, my leakage current edged up past what I can read. I have a high limit failure. So it's important to distinguish the difference there, because just because you get a high limit failure doesn't mean you got an insulation fault, okay? So just a couple important points there, because most Hipot testers these days do have these different detectors to see things. All right, let's talk about the arc detector a little bit more, because I know there's some people that are curious about it. The arc failure detector works a little bit differently than the other ones in the unit. What it's doing here, and if you've ever used our units before, you know that you can turn arc detection on or off. You don't have to use it. And then when you turn it on, you have level adjustments. You can go anywhere from 1 to 9. 1 being the least sensitive, 9 being the most sensitive. So what's happening here is 2 stages. First of all, you're turning it on and then you're keying in what level of sensitivity you want. Then what's happening is there's a high-pass filter. So the unit is looking at the leakage current wave, or the wave coming in from the return, and it's using a high-pass filter to only get frequencies above 10 kHz. As I mentioned before, these are the moments or the frequencies at which are indicative of a buildup of corona, which is kind of a precursor to a breakdown. It'll filter out all the low waves, and now all you see are these little high-frequency peaks. What it then does is it looks at the amplitude of those peaks, runs it through a comparator, and compares it to your level adjustment, and says, okay, looks like I have some high-frequency noise. Let's look at the peak of this noise in milliamps. Let's compare this to the level they set. Is it more? Oh, it is. I'm going to shut off and give them an arc failure. Now, what do those levels mean? That's a question we get a lot, too. But before I get into that, we have another poll for you guys, just with regards to using arc detection. All right, looks like our poll has closed, so I will move on. The arc settings. So this is specific to our instruments. I can't speak on any other units, but if anybody who uses Associated Research Instruments uses the arc setting, this is essentially what you're looking at. So an arc setting of 1 represents about a 20 milliamp spike with high frequency, and then 9 is about 2 milliamps. So as you can see, 9 is the most sensitive, and it's about 2.25 in between each setting. I want to point out something here that's very important. 2 things. Number 1, these arc events, they're not generally seen as pass-fail criteria by safety agencies. They are more seen as a quality thing. So just because your product fails with an arc fail, if you are using it, doesn't mean you have an insulation failure. Now, if you have arc fail on and you get an arc fail, and then you turn it off, and you go back and you test again, and you get a breakdown or something along those lines, okay, yeah, then it has given you a heads up like, hey, you might have an issue here. But a lot of times we'll get calls from customers saying they keep getting arc fails. Like, oh, I'm getting an arc fail, I don't know what's wrong. What I usually have them do is, okay, Mr. Customer, go in there, turn arc fail off and run your test again, and lo and behold, it passes. That's because the unit is picking up some buildup of corona, and it could be some significant spikes, but the insulation is actually still fine. It's still intact, and they're well within the leakage limit. So that's an important distinction to make. Again, arc settings are seen more as a quality issue and not safety agency standard pass-fail criteria. However, you may deal with a customer who wants you to use it and considers an arc fail a true failure. You know, that's something that is a case-by-case basis, and I can't speak on that. But you know, there's some tough customers out there, and they require that an arc fail is actually considered a failure, and I have run into those applications as well. So the other very important key point to our arc detectors is this is not like a partial discharge tester that gives you very accurate nanoamp or picoamp level information on the buildup of corona or where the void is or anything along those lines. This is an estimation. It's not an exact science. There are many variables involved when we're talking about the buildup of corona or arcing over or surface tracking or anything along those lines. There are many variables, including surface geometry. Am I dealing with two spherical conductors, like wires next to each other? Am I dealing with a point and a flat plane, which is kind of worst case as far as arcing goes? Cylindrical? Those all make a really big difference to when and where something will arc over, as will altitude, atmospheric pressure, even temperature can make a difference, humidity. So that's something you really want to keep in mind, because we run into situations where one customer at one site is comparing their arc settings to a customer at another site, and they're like, oh, we're getting arc failures at different times. Yeah, that doesn't surprise me. If you're trying to base your entire process off of whether your arc setting is 6 or 7, you're probably spinning your wheels a little bit. It's not that in-depth, and something you really need to realize is it's not an exact science. So that being said, I have one cool little video to show you here. And let's see here. I replicated an arc failure. So what I did was, I'm going to pause this. Between my high voltage and my return, I put a sample of Mylar because I knew that the Mylar wouldn't break down, but that I would get some surface tracking. So what I did was I put it in between those 2 points, and then I went ahead and I ran a test, and it's going to build up. And once it tracks enough on the surface, I can even hear a buzzing in this video once it gets up to 5 kV. Boom, you get an arc fail. What I did right after that is I just tested the sample with the arc fail detectors off, and it was fine. I got really low leakage. I didn't have a problem. But it was picking up that surface tracking, that buzzing of the corona that was occurring around the leads and was tracking over the sample. Again, that just points out the importance of really knowing what you're failing when you're testing. All right, very good. So that being said, we've gone pretty in-depth on the detectors. So now that we've talked about the detectors, the last thing I want to get into here is some features. Features that are going to be useful to you guys here in the field. So hopefully after this Hipot Testing 101 and 102, you have a lot better feel for not only what a Hipot test is, but how your units operate. Even if you have a competitive unit. You might call these features different things, but you might have some of the same features. Use these to your advantage. That's why they're there. That's why we built them in. You know, a lot of people consider them bells and whistles, but if you have it, you might as well use it. A lot of these features can actually help you speed up production and keep your operator safe. So there's a variety of built-in features to ensure operator safety and streamline testing. And I kind of put these into 3 separate categories. You have your safety features, your safety and functional features, and your functional features. So for safety, that would be what I say our SmartGFI and our Interlock. For safety and functional, a little mix of both, would be what I would call our prompt and hold. And then for functional, ramp high and charge low, which I will get into in more detail here. So let's look at our SmartGFI. This is pretty much on every one of our units. Some of our older instruments didn't have this. This was built in a little bit later, but all of our current instrumentation that you can find on our website right now all have a SmartGFI circuit built into it. Basically what it does is it can detect if someone is touching the DUT by monitoring the return leakage current. It kind of works similar to a standard GFI, except it's much more sensitive. Basically, if you're looking at the leakage current coming out on the HV line, and you're looking at the leakage current coming back on the return, if there is a discrepancy of more than 400 microamps or 450 microamps, the unit's assuming, hey, I'm seeing this discrepancy in current, someone is touching the DUT, shut down immediately. As you can see in that picture, it's working. That guy's pretty happy because he's not dead. So what we're doing, and I tested this in front of people. I've grabbed the high voltage lead. I've put the return lead in the proper spot on ground, and I will push the test button while holding it, and the SmartGFI trips before I can even feel anything. Number one, please don't do that. I am not advising that you do that. I am a trained professional when it comes to Hipot testers, so just like you see at the beginning of a Jackass video, do not try this at home. Will I be putting out a video where I'm doing this? No, probably not, although I'm sure some people would like to see that. Maybe I'll think about that later. Anyways, on all of our previous instruments, or the ones that we have, except the Omnia 2 works a little differently. So all of our units have a set built-in 450 microamp trip limit. So if it goes over that, it's going to trip out. And you can turn SmartGFI on or off. The reason for that is we do have certain customers that have Hipot units on a production line where their unit comes on a conveyor belt, and that conveyor belt has a solid ground. What can happen is you get stray current to ground anyways, and the unit thinks somebody's touching it, but in fact all that's happening is you're getting stray current going to ground as a result of the setup. In certain cases, they have to turn the SmartGFI off as a result. What we did on our Omnia 2 series, we actually made it adjustable. So you can set it as far down as 400 microamps or as high up as 5 milliamps to help accommodate some of those customers. So now those customers that have that problem can compensate for it. They can adjust. They can still take advantage of the SmartGFI, but at the same time have that extra measure of operator safety. So real basic circuit. It's not too complicated how this thing works, but it's a great safety feature, and we highly recommend you utilize it. If you go into the system setting on your units, you go into your system settings, and you'll see SmartGFI. By default, every one of our units has it on, so you got to turn it off if you want it off. Interlock. This one is a pretty straightforward one too. So you can see there, if you see letter B right there, that's pointing to the Hipot tester. And as you can see, I kind of did a little expand out bubble on the back of the Hipot tester. You have a remote input and remote output. Our interlock is located between pins 4 and 5 of the signal or remote input. Why do we have this? Well, what you can do, as you can see in that picture there labeled H, is we've wired pins 4 and 5 to the door of an enclosure, a safety enclosure. So you have pin 4 on one side of the door, you have pin 5 on the other, and something like, let's just say, a magnetic switch. So as soon as that door opens, it breaks the interlock contact, and the unit will shut off, boom, immediately, like fast interrupt. Really quick, we'll shut off and basically say, hey, your interlock is open. I'm not outputting voltage until you close that door or you short those pins. Not everybody uses this to wire up a DUT enclosure. You guys, whoever's used our instruments, I'm sure you're familiar with the interlock key. You have to slap that into the back of the unit, and basically all that does is it short pins 4 and 5 on the instrument so that you can go ahead and run your test. It's kind of like a car key. The Hipot unit's not going to turn on unless you have it in place. I know that there's a lot of customers that don't realize this because I get calls, and I answer the phone. My unit's not working. My first question, 100% of the time, hey, is your interlock back there? Because 50% of those is, in fact, it was not. So you do have to have that in there, or you can wire it up like you see in this safe operator setup here. So another great safety feature to take advantage of if you can. So here's more of what I would call functional and safety. And the reason I put it, I categorize it as safety as well, is you can use something like a prompt to keep your operators safe. So what is a prompt? You basically add it to your sequence as an instruction. So let's say I have a 20-step test, and on step 5, I need the operator to disconnect and connect to a different circuit. Well, I could add that as a prompt. I could say disconnect HV lead and apply to pin 2. And the nice thing here is that the unit will stop the sequence, the prompt will come up and give the operator instruction. The operator has to push the test button to proceed. So it's pretty much almost a foolproof way to make sure that your instruction carries out properly, but you can also use it as a safety feature. For example, the very first step of your sequence could be stand back, make sure you're not touching anything, and press the test button. Just as a quick reminder, oh, am I in the right place here? Am I too close to an HV lead? Give you a quick gut check to make sure that everything's all right. So most of our units, the Hipot 3, I do not believe has this feature, but the Omnia series has it. The 620L line check unit has it, and I believe the Ultra 3 or 7600 series units might have prompt and hold as well. So something that you might want to take advantage of if you aren't already. Now let's get into some fun functional ones. The two biggest ones that stand out to me as functional, and we have others as well, but these are really ones that come in handy a lot, are the ramp high and charge low. So earlier during this webinar, we talked quite a bit about setting leakage limits. That's great for AC Hipot testing, because for AC Hipot testing, you're usually going to get a pretty significant value just for the fact that you have a lot of capacitance. However, what if you're running a DC Hipot test? What's going to happen during a DC Hipot test? And you may recall some of this information from Hipot Testing 101. At the start of a DC Hipot test, again, remember, you're testing a capacitor. So you're going to have very similar behavior as if you applied a DC, took a 9-volt battery and put it across a capacitor like you might have done in school and measured the response curves. At the start, you're going to have an inrush current. You're going to get a spike of leakage current, but then it's going to kind of die off. It's going to trail off, and once the installation is fully charged, your leakage current is going to drop to near zero. That presents two problems. Number one, what if for your DC Hipot test you have a high limit? I'll just throw out an example. UL17, I don't want to say the wrong number here. I think it's 1703 for flat plate photovoltaic cells, solar panels, stuff like that. They have a high limit for their Hipot test of 50 microamps. That's not a lot of current. Well, what if you failed that test because your inrush, you have a really quick ramp, and your inrush current was too much? Sure, you could change the ramp up to 5 or 10 seconds, but what if you're dealing with a production line where you're doing thousands of units a day? 5 to 10 seconds makes a big difference. We have a feature called ramp high on our units, and you basically, for a DC or an IR, or what I mean by IR is installation resistance test, for a DC Hipot or IR test, you can turn it on or off. It's neat because if you turn it on, it basically ignores the inrush current value, so ignores the high limit during the ramp up, and only pays attention once you reach the dwell cycle. If you still have elevated levels during the dwell cycle, it's going to shut off, but it's going to ignore those little spikes. So number one, then you can have a really quick ramp up, as low as I believe 0.1 or 0.4 seconds on a lot of our units, and at the same time take advantage of that for a DC Hipot test. So that's neat because it can save you a lot of time on the production line. The other one is charge low. And what this does is it kind of compensates for the fact that it's really difficult on a DC Hipot test to set a low limit. Because once you've reached if you've already ramped up and now you're in the dwell, your cap is charged, your installation is charged up, so you're not going to read much current at all. You might be in the nano or picoamps, and the unit can't detect that. I believe 0.1 mics is the lowest we're going to go. So how do you set a low limit? You're going to get a false failure every time if you try to set a low limit. That's what charge low does. What charge low does is you connect up your circuit as you would the test. You let the unit run a little quick diagnostic, and basically what it does is it looks up the charging current, takes half that value and says, all right, with this product I should be getting at least this much. So basically these allow you to compensate for limits for a DC Hipot test, because that can be a little bit trickier. So let me show you a quick example of what I'm talking about here for the charge low circuit. Oh, wait, that's not the one I want. I want to set it first. All right, so basically what I've done here is I'm setting up a test, and I have my DUT connected. It's a little fan. You can see I have return on the chassis and high voltage on, line and neutral. And I have the power switch on. That's very important. Always have your power switch on. So I have 1200 volts DC, and you can see the charge low value there. I'm going to push the test button. It's reading, and I know it's a little washed out there, but what I did was I went to the charge low parameter, I hooked up everything, and I pushed the test button, and it gives me a value, 2.8 microamps. So the unit is saying, all right, with this TUT at this test voltage and that ramp up, I should have at least 2.8 microamps. So what if we don't? So here's the case where the operator forgot to put the return lead on. It knows it. It right away is saying, hey, look, you've gotten a charge low failure. I know I should be getting at least 2.8 microamps during that ramping, and I didn't. I got 0. I'm going to fail. So it's a good way to give you a gut check and make sure your operator is doing things properly as well. Just the same thing as an AC test and a low limit. So we covered a lot of information today, and I'm leaving about 5 minutes left here for questions. But if you want a copy of the presentation, let Jim know. He can send it over to you. Don't forget to check out our website. We have a lot of materials. We have white papers, technical articles, training documents, as well as this webinar archive. So if you're training new guys, you got a line of guys coming in, or new engineers, or whatever the case might be, you just want a refresher, check us out. Also, follow us on YouTube and LinkedIn. We're always updating information. On YouTube, we are coming out with a series of quick start videos for our entire series line. So say you just bought a new 3700 unit or a new 3130 ground bound tester. We have quick start videos up there. Gives you the nice down and dirty way, how to connect it, how to run it, how to set up your test. So it's really handy from that regard. And then LinkedIn, you can also get updates from us as well. So feel free to check us out. I'm going to leave the floor open for a few minutes to any questions we might not have been able to get to. One important point, if you have a very in-depth question, which I really can't get into in a 5-minute time span, just reach out to us. Email info@asresearch.com or email Jim. You can also feel free to email me directly. That's nickp, N-I-C-K-P as in Peter, @asresearch.com. I'd be more than happy to talk in depth on it if we need more time to do so. But at that, I thank you very much for attending the webinar. I hope you found it useful, and attend our next one in June.
Hey, Nick, we do have 2 questions that I think actually would benefit the whole, all the attendees. If you
Great.
could review them real quick. One has to do with repeated Hipot testing. Does it damage the device that you're testing?
That's a good question, and it's something that comes up from time to time. And personally, I think there's a lot more data that needs to be gathered on this front to really ascertain what the situation is here. And what I mean by that is various voltage levels on various levels of insulation and repeated Hipot testing on them. That being said, from the research that I've done in the lab and that I've done with Dwayne, and for anybody who doesn't know Dwayne, he's been one of our Hipot testing gurus. He's been with the company for 45 years. If there's an application out there that he hasn't seen, it doesn't exist. So what we did was we ran and cycled various DUTs with our Hipot units over and over and over and over and over again. And what we found is if you're Hipot testing within the spec, and I want to put an asterisk there, within the spec is very important. If your spec says, hey, you got to Hipot test this at 1240 volts, that's what we did. We did it at 1240. So within reason is basically what I'm getting at there. And we ran 10,000 Hipot tests on the same product. And then we went ahead and measured leakage current on the 10,000 tests. The leakage current on test 1 and test 10,000 were essentially the same. That tells me that no, if you're testing within your specified limits, within what the standards are stating or what your internal company standards might state, with what you know your installation can handle, repeated Hipot testing should not damage a product. However, problems can come into play if you say, oh, this guy said repeated Hipot testing doesn't damage the product, I'm going to go and test this thing at 3,000 volts. But your spec says 1240 volts. Well, guess what? Voltage is a force. So if you're going to go over what is recommended, yeah, you're going to have a problem. It's like if somebody says, yeah, this picture frame can take nailing in with a hammer into the wall and whatnot, and you say, well, I did it with a sledgehammer and it broke. Well, yeah, of course it broke. You applied way too much force. So keeping it within reason, what we found is that no, repeated Hipot testing does not seem to damage or compromise the installation. Was there another question?
I got one more. It actually has to do, Nick, with yeah, there is. I think you touched on it briefly when you were going through like setting up safety features in SmartGFI and whatnot, but it would be good for the whole group to maybe review it again in reference to ESD, the use of ESD devices or preventative measures at the same station as a Hipot test.
Gotcha. Yeah, that's a really good point, and I'm glad that somebody brought that up. First and foremost, I'm going to say it right off the bat, these stations are not supposed to be mixed. Do not use ESD stuff with Hipot stuff. Because think about what you're doing. With ESD, you're grounding everything so that you can isolate electrostatic discharges so that, for example, I don't walk up to a circuit board and touch it and have a static charge and now I fried an IC. So I get ESD controls and measures. It makes sense. I know why they're out there. However, you're grounding everything out. Do you really want to be grounded out when you're working with a unit that can output 5,000 volts at 100 milliamps? You basically just put yourself at a low impedance ground potential. Current loves low impedance ground potential. So that leakage current is going to want to follow that track. Yes, granted, a lot of these Hipot units have a lot of safety features, but in general, do not use these at the same station for just the reason I mentioned. It's a safety thing. In fact, when you're at a Hipot station, we actually recommend you use isolating materials, like an isolating insulation mat that the operator can stand on to isolate them from a ground potential. So ESD stations, in my opinion, are really designed to protect the DUT or whatever is at the station, like a circuit board, whereas Hipot testing stations are designed to protect the operator. A lot of times when you're dealing with ESD components, you're not really dealing with high voltage stuff. A lot of it's like boards and things along those lines, which are low voltage pieces of material. But now when you're talking about Hipot, now you're talking about really high voltage on products, and that can be dangerous. So I think it's important to make that distinction. Do we have any others?
Right now, Nick, I think you covered everything. There's a few others, but they're really in-depth. Probably would take up a good portion of your time.
Sure. For anybody who's got more in-depth questions, I would recommend you email us, info@asresearch.com, and that'll be filtered down to us. And we would be more than happy to get in-depth on those topics. But again, I really appreciate everybody attending these webinars. We hope you find it useful. Please take the survey afterwards so we know how to improve our material and what you guys want to know about. And hopefully we'll see you next month.